I'm glad to welcome you here for this André Eisenstadt lectures. So these are the most prestigious lectures of the Centre de Recherche Mathématiques. They started at the beginning of the 70s and are named for a donor who was interested in mathematics. He had a thesis from ETH in physics, but he became a businessman, and so he supported the CRM later on. There are many famous mathematicians who gave this series before. So among them, Bhargava, Tao, Yokoz, Okunkov, Guionnet, and many others. And the series consists of 3 lectures. The first one is for a more general audience. And we are delighted to have here today Isabelle Gallagher from Paris 7. And Isabelle obtained her PhD at the Université Pierre et Marie Curie in 1998. She was an ICM invited speaker at the 2014 ICM. And she was awarded the Silver Medal of the CNRS in 2016. And she will talk about the mathematical analysis of dilute gases. And I leave it to her.
So thanks very much for the introduction, and thanks to CRM for inviting me. I'm very happy to be here again. I apologize for a lot of you here who've seen me already too much, I guess. So this is actually the 3rd of my talk, so it's a bit strange. We're going to have the trailer after the movie in some sense, but I hope it'll be okay. I apologize for some of you who know everything I'm going to talk about very much. Maybe it'll ring a bell sometimes. You'll think, oh, that's what she was saying last time. Now I understand, maybe. Or now I still don't understand. So this talk is intended mostly for people who are not in the, well, especially for people not in the field of PDEs in general. There will be PDEs because I have to write PDEs. I'll try to not to be too technical and just explain a little bit the context of what we're trying to do. Okay, so I apologize for people who get bored. I'm sure it has lots of nice things to do. And I just want to say that this conference is great. So thanks to the organizers. I'm having a great time. I think we all are. And so, yeah, thanks for the semester. And especially these 2 weeks are really very interesting so far. Anyway. Okay, so I'll be talking about the derivation of the Boltzmann equation. I'd like just to convince those who don't know here that in some sense, the Boltzmann equation is a way of writing down a PDE, an easy, in some sense, equation to model something very complicated with many agents, many particles, as we saw in David's talk and lots of talks before. And in some sense, when you have a physical system, whatever it is, with a lot of agents, a lot of actors, it's very complicated. There's a lot of what we'll call entropy later on, disorder coming in. And the Boltzmann equation is, in some sense, quantifying maybe a little bit of this disorder. So let's explain a little bit what a disorder means. So I was not allowed to take a picture of my teenage daughter's room, but it's good for you because it's even worse than that one. So it's just an experimental fact, right? If you don't act on something, it's going to get havoc, right? That's what we usually, well, physicists would say entropy increases. I would say disorganization increases. And this is probably linked, and we'll try to explain why, to irreversibility. For instance, if I go and see my daughter and I act on her, not on her room, I'm not allowed, I can act on her, then she will act on her room. And then I can put a camera and see what happens, right? And I guess in about 2 hours, this happens again, right? But if I take that movie and I play it backwards, then obviously it's not reasonable, right? I would never imagine her room getting orderly. Okay. So there is an arrow of time. Okay, disorder is definitely something which is irreversible. You can't hope for a better situation to happen, unfortunately. This is an experiment in some sense. It's a numerical experiment you can find on the web, which is called usually often the Ehrenfest experiment or even paradox. And so I'll play you a little movie here. Well, just to tell you what's going to happen, you have 2 containers which are related, linked together by a small corridor, okay? And at time 0, I put about 200 particles on one side. Okay, and then the particles are allowed to move freely. They actually ignore each other. So whenever they cross each other, they don't collide. They just go one on top of the other. They ignore totally the existence of the other particles. What they do not ignore, of course, is that they are in a container. So they're going to hit the boundary of the container and just have some kind of a strained movement. And sometimes, pretty often actually, they will find themselves in the corridor and go to the other side. Okay, and what we're going to look at here is how many particles end up in the other side. So of course you can't see the numbers, we don't really care, but you had 200 at the beginning, and then the number here is decreasing. Of course, not in a totally smooth way. This number here is increasing, and you see that pretty quickly you had just about as many particles on each side. Okay, so some particles are going from left to right, others from right to left. And so I shouldn't, I guess, not be showing the board here. Anyway, and so pretty quickly you have essentially 100 particles on each side. Now, as I said, each particle has a movement which ignores totally the others. Okay, so if you forget all particles, just remember one, just look at one. So imagine there's only one particle here, and then imagine I'm playing that movie in the other direction, okay, rewinding the movie. If you have only one particle, there's no problem. You can play the movie in one direction or the other, nothing strange is happening, okay? Now, if you take this movie here with the 200 particles and you play it and you rewind it, then everything will be fine, and then suddenly all the particles will be in the same, it's definitely not physical. The Ehrenfest paradox is saying if I have 1, 2, or 20 particles, then this film is reversible. But then if I have 200, it's not, but still they're ignoring each other. So what's going on? Okay, and this is something we can understand, of course, very easily, but let me just give you that in another way. Here we've, what people have computed here is how many particles are on the left-hand side with time. So at every second, you count how many particles are on the left-hand side. And so here I started with 4 particles, and we count about 100 times what's going on. And you see that pretty often all the particles are, all the particles, can I write here without, all the particles are on the left, n is equal to 4. Sometimes all are on in the right, since n is equal to 0, and then sometimes they're all 1, 2 on each side, n is equal to 2. Okay, nothing strange happening. Now, if you have 500 particles, you see obviously something is happening, that very quickly there are about 250 on each side. Okay, and that will happen for a very, 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 very long time, obviously. So of course you have fluctuations around 250, but essentially you have as many particles on one side as the other. So this is what we're mentioning before as irreversibility, right? You really see an arrow of time in this picture. So actually I learned yesterday from Alex, who's somewhere here, I can't see where, that, I mean, most of you know that there's this theorem called the Poincaré theorem, telling you that at some time, everything will happen as exactly or almost exactly as where you were at time 0, meaning at some time, you will have all the particles on the left. But the sometime you can compute quite easily, and you find it's essentially 2 to the n, where n is the number of particles. So just if n is 10 to the 23, we won't be here to see that happen. Okay, so this I showed to classrooms. I know you're not, this is a general audience, but a little bit more than college students. But anyway, I'll just show you that. I like to show that to explain that, of course, what happens here is that it all depends on the number of particles you have that we saw before. It all depends on what you see at the human level compared to the atom levels, right? So if you decide that your particles are not identical, if you can distinguish them, you can put colors on them, then you can start counting how many microscopic situations you have, how many different ones, compared to the macroscopic situations. So macroscopic is just saying how many particles do I have on the left-hand side? I can have 1, 2, 3, or 0, up to n. Okay, and the microscopic is saying how many configurations do I have in total. So it's easy to count when there are a few particles that, for instance, if you have 2 particles initially, then you have 4 microscopic and 3 macroscopic. Okay, if you have 3 particles, then you have 4 macroscopic, since you can have 3, 2, 1, or 0 on the left-hand side, and you have 8 microscopic. And then since we know what's going on, we know that if you have n particles, then you have n plus 1 macroscopic configurations and 2 to the n microscopic configurations. Okay, and that's why you have to wait for 2 to the n seconds, essentially, right, to get exactly back to where you were. Right, so what's the relation between n and 2 to the n? A log, right? So the logarithm has something to, a role to play here. Let me explain to you, for those who don't know, why the logarithm is a good function to measure disorder. Okay, so okay, so let me give you any system, like the one we just saw, but any system, and assume that you have a countable number of microscopic states and a countable number of macroscopic states. Okay, and what I'll define here as pi is a function of the microscopic states, which tells you what you perceive. Pi of n is what you perceive, right? So in the drawings I had before, the microscopic states are in lines, and what you perceive are just each line. Okay, 1, 2, 3, or 0 particles on the right. And now let's just give a definition of uncertainty, okay, or disorder. Uncertainty will be a function, we decide, it's a function of the cardinal of the inverse function, so pi minus 1 of W, meaning if W is a macroscopic state, okay, I decide that the disorder or uncertainty is a function of pi minus 1 of W. Okay, that's something we decide. Now, what I want to see is that entropy is actually a log of this function. And the reason is simply the following. If you do 2 independent measurements, then you expect uncertainties to add up. Okay, but on the other hand, of course, if you look at the number of the cardinal of a couple W1, W2, then it's the product of the cardinals of CW1 and CW2. Right? For each one, you have all the others possible. So the function uncertainty is a function of the cardinal, which satisfies this property, and this function is additive. Then uncertainty has to be a logarithm. Okay, and that's what Boltzmann found. You see here his tombstone in Vienna, where it's actually engraved that entropy S is k times the logarithm of the uncertainty of CFW. Okay, so that's a very famous formula by Boltzmann. So we'll be talking about Boltzmann quite a bit in the following, but maybe the only thing we can remember here from what I've been talking about is that I was talking about irreversibility, and that's clearly linked to the scale, right? We saw that in the Ehrenfest paradox. If you don't have many particles, everything's reversible. If you have many particles, because we are at a human scale, then things look irreversible. It's just a question of scale. But since the number of particles sitting in this room or in a glass of water or anything is gigantic, 10 to the 23 or 24, then irreversibility comes in because there are so many particles. If you want to look at a large particle system like the air in this room, how is it moving in time, then what we'll feel about this particle system will be irreversible. Okay, so what we could do, of course, to start with, and that's what we've been doing a lot this week, is write down equations for each particle, because that's easy to do. Okay, so for instance, so now let's just write down things that are as simple as possible. So I'll assume that my particles are just identical hard spheres. So for instance, the gas in this room, I'll just pretend it's made of atoms, which are all hard spheres. Okay, which is not very physical, but it's already complicated enough. And so what I'm saying here is that the hard spheres are moving in straight lines. Okay, so that means the time derivative of the position is just equal to the velocity. And I'll assume here there are no forces, just to make things simple. And actually, it's about all we can do. So that means the time derivative of velocity is 0. So my particles are going in straight lines, but of course, what can happen pretty often is that they collide. When they collide, I'm going to give a collision rule, which is just saying that, so I'd like to be able to write here. How come? Oh, yes, I can. Great. Right, so the collision rules are here. Okay, so I'm saying that the incoming velocities, which I wrote here, are computed according to the outgoing velocities, or the other way around, it's an involution, by this formula. So you really don't care about the formula if you've never seen it. It's just the Descartes laws, as usual. All you can remember, if you want to remember anything, but you don't really have to actually, is that the momentum and energy are preserved. So these are elastic collisions. That's sort of important, actually, in what we're doing. Okay, so this is the model you can write down. It's easy to write down, just Newton's laws, 1746 or something. So it's old equations. There's nothing wrong with them, except that actually we do not care where each particle is at each time, right? At our human level, I couldn't care less if particle number 10 to the 23 is here or there, right? But I can write down this equation. So the problem is, one, we don't really care, and two, probably another problem is there are much too many equations. I mean, in dimension 3, you have 6n equations, okay, and n is large. So the question we want to address is there a way to model this system by something easier, which will be a PDE? So we have here ODEs, many ODEs. We'll replace many ODEs by one PDE, which will be nonlinear, okay? And of course, this PDE won't have all the information, but at least information we might be interested in at our level. So for instance, just to give you an idea of this, if I open the door and there's some wind or something outside, there'll be some air going in, okay? And so I'll feel something, I'll feel the velocity of the air, I'll feel the temperature, which is of course related to those equations, but not directly. Okay, the same way if you see the air at the back of this room, it's not moving, but each particle is moving. So we had to understand that in some sense. So one remark maybe I haven't made here on the Newton's laws is that those laws are reversible. Okay, you can play the movie any way, it works very well. And what we've understood probably from the beginning of this talk is that the PDE we're going to write might be irreversible. If I open the door, if I close it, these are different, right? So I should see that in the equation. So the question we're going to try to address now is how you can extract from this huge system of ODEs one nonlinear irreversible PDE. So that question was asked by Hilbert at the second ICM in Paris in 1900. And so he was asking in his sixth problem, can you develop in some mathematical way some limiting procedure going from particle systems to fluid mechanics? So actually it's even more than what I'll be talking about the Boltzmann equation here, a little bit about fluid mechanics. So actually what I put here under with little dots is he was actually saying you can also use Mr. Boltzmann's book to help you. So we will actually use Mr. Boltzmann's book, or at least his equation, to help us go from particles to fluids. So the Boltzmann equation, which will be probably the most important equation in this talk, relates essentially to the number of particles you can find at time t sitting at position x with velocity v. Okay, so you keep the notion that each particle has a position and a velocity. So again, I didn't say that before, but the position was just the center of the hard spheres. Okay, so I have n particles numbered from 1 to n, they're indistinguishable. And I want to know typically how many particles I have in this, maybe a small region around x, a small region around v at time t. And I call that f. I assume I want to prove that it's a density depending on t, x, and v. And Boltzmann wrote down an equation for this density. Now, why is this density interesting? Because actually, you can't really compute it. I mean, from a physical point of view, you don't really have access to this f. But what you do have access to are averages of f. Okay, so essentially, if you take f and you start taking an average with respect to all velocities, then you get the density of your fluid. If you take your f and you average it against v dv, then you get the average velocity of your fluid, the one you really feel at our human level. Okay. Now, if you average against v squared, you get something like the energy or the temperature. Right. So the fluid equations you're going to find in the end, hopefully, are obtained by taking this Boltzmann equation and taking averages. And with a bit of luck, those three quantities, density, velocity, and temperature, will be related by a fluid mechanics equation, like the compressible Euler, for instance, equations, very well-known equations, maybe Stokes, etc. So that's the goal. That's what Hilbert was suggesting. Start with your particle system, use Boltzmann if you like, but in the end, find a fluid mechanics equation. Now, here's the Boltzmann equation. So for those of you who've never seen it before, let me go slowly maybe through the different terms of this equation. So as I promised, this is a PDE. There's one PDE, okay, which is sort of modeling my 6 times n ODEs we had before. It's an approximation in some sense we'll be talking about later on. But let me just explain why it's very reasonable that this PDE should be exactly that one. Okay, so remember f is telling me how many particles I have at time t with position x and velocity v. So the left-hand side of this equation here is a transport equation, right? V is the velocity, x is the position. So if you had no right-hand side, okay, just ignore the right-hand side, then you would just be saying all particles are moving in straight lines. They have collisions, and the collisions are binary, okay? So that I didn't really discuss, but it's not hard to prove that the measure, say, of initial data says that you have more than 2 binary collisions would be a 0. So we just forget about any more collisions than binary collisions. So that's why the right-hand side here is nonlinear, but it's bilinear. Okay. Now let's go a little bit through the right-hand side, which looks pretty awful, I guess, if you've never seen it before. But you get used to it, I guess. Okay, so let's see. So I said it was binary. So now we understand why. I said x is the position of my particle. So I'm counting how many particles have position x and velocity v. So what can happen dramatic would be that a particle of velocity v hits another one. And when you collide, your velocity changes. Okay, so that means here, my particle of velocity v has hit a particle of velocity w for any w. Okay, you're integrating over the whole of Rd. Okay, and then if you do that, then you lose, that's why there's a minus sign here, you lose a particle of velocity v. On the other hand, what could happen is that a particle of velocity v prime, which is, remember, incoming velocity, hits a particle of velocity w prime, which are related to v and w through those formulas here. And then you're very happy because you've created a particle of velocity v. So that's why you have a plus sign here. Okay, f is non-negative. F is a probability distribution. So now I guess we're pretty happy with those 2 terms. We understand them pretty well. They're reasonable. What about this guy here? Well, so this is computing an angle. Omega is an angle here, and v minus w are the relative velocities of my incoming particles. And omega actually will be a deflection angle. So what happens here is that if v minus w is 0, which means my particles are moving in a parallel way, then they'll never collide. Okay, even if they're touching, they won't collide. I mean, they're just, nothing's going to happen. So that's why this is 0. Okay. On the other hand, if my particles are orthogonal to their, if the velocities are orthogonal to the relative position of my particles, then the collision will be as hard as possible. So that's the maximal thing that can happen here. Okay, so that's not a proof, but it sort of tells you it's not totally wrong. Okay, and okay, we'll see later on why it's exactly that comes out, but I guess now we're sort of happy with almost all the terms of the equation. What I haven't described here is this 1 over alpha, which I've never talked about before. But for the moment, you could ignore it, but you could imagine that alpha is going to get very, very small. If alpha is getting very, very small, that means that this Q of FF is getting very, very large. I put something very large in front of it, which means I'm counting a lot of collisions. Okay, so just remember this alpha will pop up at some point. For the moment, it's just a factor I put in front, a scaling factor, counting the strength of my collisions in some Boltzmann equation, 1872. Let's talk a little bit about properties about this equation. So it comes from physics. It comes from a very simple physical problem. It should inherit some physical properties of my original Newton's laws. If it doesn't, then there's something wrong with it. And so what we like to do in PDEs, if you give me a PDE, I want to find conserved quantities. And to do that, what I'm going to do is multiply the solution by anything, what I like, integrate by parts as many times as I can. So we like that usually in analysis. And then if you get 0 on the right-hand side, that means on the left-hand side, things were transported. Okay, if the right-hand side goes to 0, when I say cube FF multiplied by something, if that gives you 0, then on the left-hand side, F times that something was just transported. So conserved in some sense. So a tiny bit of algebra actually here. Right, I multiply by phi of v, I integrate in v, and then I notice that w and v are totally symmetric. So I can put 1/2 of 5v plus 5w. And then I notice that I could change v and w for v prime and w prime. Okay, that would have changed the sign here. This plus would have become a minus if I change incoming into outgoing. And so if I do that, I get a minus sign here. And so once you've seen that, you say, well, for the left-hand side to be 0 for any f, I want a conserved quantity for every f, of course. It doesn't make much sense. So for this to be 0 for any f, I need this quantity here to be 0. Okay, so there's one good example where this is 0 is when phi is a constant. 1 plus 1 minus 1 minus 1. Okay, there's another case where this is 0. That's when phi is identity, because of conservation of momentum, v plus w is equal to v prime plus w prime. And then the last case when this is 0 is when phi is v squared because of conservation of energy. Okay, and it's actually a theorem that it's the only case. It's the only case you can have 0. Right, so we recover with the Boltzmann equation the conservation of mass in the sense that the integral of f is conserved, of momentum, integral of fv is conserved when you integrate against x and v, and the integral of fv squared when you integrate against x and v is also conserved. What else is conserved? Well, you can play the game of replacing phi by log f. Remember the log we liked at the beginning of this talk? Well, we still like it because x log x has convexity properties that tells you that q of ff times log f will always be negative. Okay, so that tells you in particular that the time derivative of f times its logarithm is always negative, non-positive. So if my daughter knew anything about mathematics, she'd tell me, see, entropy is decaying, so my room is getting in good shape without my acting on it. But no, because the physical entropy is actually minus this one. Okay, so it is telling you, so the Boltzmann equation does have increasing entropy. And you see, because this has a sign, it's not equal to 0, then the dynamics is irreversible. Right? So if you change the arrow of time, then you change the sign of this thing, and Boltzmann doesn't want that. Boltzmann is telling you, you have a sign here. So this is Loschmidt. So maybe some of you know, I guess a lot of you know that there was a huge controversy at the time between the fact that Boltzmann is irreversible, the particle system is reversible. Why is that? So we've sort of understood, and by what I was telling you before, and we'll see that a little bit later also. This is the Boltzmann equation in a nutshell. One maybe useful comment, I might be using that a little bit later on. If you want to know what are equilibria, that's also an important thing in physics, right? What function doesn't see anything in the equation? What's conserved by the equation? Well, what you need in particular is that the entropy has to be a constant. If you have a solution which doesn't change, and the entropy mustn't change, that means that log f has to be like phi before, either 1 v or v squared. And since f is an L1, actually it has to be like log f has to be like minus v squared for it to be integrable. So in the end, what you get is our Gaussians. It's the simplest one. You could have coefficients depending on x maybe here. But let's make this the simplest equilibrium possible, which is this Gaussian here. So those guys are actually canceling each term separately of the equation. Okay, so the last thing I can say about the Boltzmann equation is, can we solve it? Okay, that's an important problem, I guess. To give me a PDE, I'd like to solve it. What does solving mean? That means if you give me initial data, I'd like to say there is a solution associated with that data. If possible, it's unique. If not, it's not so interesting physically, I guess. And if possible, it's stable. If it's possible, it lives for all times. If it doesn't, what happens at blow up, etc. So actually, not very much is known on the Boltzmann equation. I guess for those of you who might know the Navier-Stokes equation, it's about the same kind of results you can prove for Boltzmann. Just change the function space around, but essentially you can prove exactly the same type of theorem. The first one is telling you, if you give me initial data, which is nice enough, controlled by a Gaussian, for instance, then for a short time, I can construct a solution that is still nice enough. Okay, so here I've said the decay rate has been divided by 2. You can put anything instead of the 4 here, right? Just you give yourself a target, and then you have a time on which you can solve the equation up to for a solution that satisfies this target value. Just a typical example of a well-Poseness theorem. If you're sufficiently close to equilibrium, then you stay close to equilibrium for all times. So all those theorems are very poor, weak theorems, right? It's the same for Navier-Stokes. If you do nothing, initially, if you look like nothing, then you stay looking like nothing for all times, right? But if you don't know, if initially you're anything you can't really control, you don't look like 0 or like a Gaussian, then you only have a solution for a small time. And no one knows what happens beyond that time. Now, if you remember that entropy is conserved, also mass, energy, and momentum, actually, you could say, well, those things don't blow up. So please use that information, right? If you want to solve the equation. So you can try to use that information, but then you can't use the Gaussian anymore for all kinds of reasons we could talk about separately, I guess, but it's sort of always the same problem. So you can have global solutions. It's very hard actually to prove, but you can prove there are global solutions which have a finite entropy for all times. If initially you have finite entropy, but you have no idea whether they're unique or not. Okay, they're actually not even proper solutions, not even distributional solutions, they're renormalized solutions. Okay, so that's essentially the picture for Boltzmann. If you want to remember anything about this, you have local and time solutions for any initial data in some sense, at least smooth enough, with enough decay at least. Global, if you're close to a Gaussian, we will be talking about later on. And unique. And then if you just have an entropy bound, then you have global solutions, but you don't know if they're unique. Let's go back to our original problem. So Hilbert was asking, can you go from particle systems to fluid mechanics? Okay, so that was the question. So now we go from to, that means you have to find limits in some sense. He was telling us to do that. So the limits we'll be using are, I'll assume the number of particles is going to infinity. I have to do that because I know if I only have 3 particles, nothing will happen. But then if my number of particles is going to infinity, maybe they should shrink. If not, I'll have a little bit of a problem with room. Okay, so their diameter is epsilon. I'll let epsilon go to 0, n go to infinity. And then if I want to remember there are a lot of collisions, remember that was at alpha in the Boltzmann equation, I'll let alpha go to 0. I have 1 over alpha Q of ff, I'll let alpha go to 0. So that's the plan. Take those 3 limits in some way or another and try to find fluid dynamics. So I said one way or another, it's not exactly in any way or another. What we're going to assume here is that essentially one particle is going to cross another one, will meet another one in time 1. Okay, just 1 or 2 or 3, or maybe 1 over alpha actually. And here, if I look at one particle, if I want one particle to meet roughly 1 over alpha particles in time 1, that means that n times, n is the number of particles around me, or n minus 1, times the volume of the cylinder I'm going to cover in 1 second, if I have velocity 1. That should be equal roughly to the number of particles I want to cross. Okay, so this is known as the Boltzmann grad scaling. If alpha is equal to 1, that's the usual Boltzmann grad scaling. Now I'm interested in alpha going to 0. I want a lot of collisions in the limit. So this is the scaling you should use. You notice that with this scaling and a fixed alpha, I have a dilute gas. Okay, so my gas is a dilute. I'm using the scaling here, whatever alpha, and then question, can you prove that the particle system in some sense converges to fluid mechanics equations? So as far as I know, the answer is no, I guess. There's no theorem, to my knowledge, going from particle systems to fluid dynamics, unless you change a little bit the initial problem you had, the particle system, and you decide to put some noise in the system. For instance, if two particles collide with some velocities, and the outgoing velocities, you're going to put some noise in it, vanishing and going to zero with epsilon, but still a small noise. So people here, some people here are very good in probability, so they'll say, oh, I'm happy if there's noise, and I'll be able to prove that theorem. I'm hopeless in probability, so for me, it's very hard. But I know that you can do it. Okay, essentially, I mean, if you have noise, you have ergodicity, things get chaotic for reasons that are not due to the particle system itself, but thanks to the noise, actually. And that helps you a lot. And so you have lots of results providing fluid mechanics equations in that setting with noise. Right, so what we want to do is not put any noise initially, but still find fluid dynamics. And we're going to do, as Hilbert said, use Boltzmann. So we're going to do a limit in two ways. First, let's get Boltzmann in the Boltzmann grad scaling with a fixed alpha. Okay, so that's this here. Okay, then when we're done with that, when we found Boltzmann, then let alpha go to zero and find fluid mechanics. Okay, so it's a two-step proof and no noise. That's what we hope anyway. So the first thing, well, one thing you can do is first go from Boltzmann to fluid mechanics. Okay, and then we'll see later about particles to Boltzmann. So there are a number of results that are known to go from Boltzmann to dynamics. Essentially, if you like Navier-Stokes, which I like, so I like Navier-Stokes and compressible Navier-Stokes, you can prove that the Boltzmann equation does converge. The solution to the Boltzmann equation, once you've taken averages, converges to a solution to the Navier-Stokes equation in all the settings I told you about before. So for instance, if you take smooth initial data close to Gaussian, okay, like this here, then you converge, then you converge to smooth solutions of Navier-Stokes, small solutions close to zero. Okay, so that's the thing that goes with. And if you take renormalized solutions of Boltzmann, then you converge to weak solutions, Millet solutions to Navier-Stokes. Okay, so you have to let alpha go to zero, and actually to do that, you even need to let time go to infinity. You have to rescale time to get people who know that diffusive regimes. But okay, so you have to wait for a very, very long time, like 1 over alpha. Let alpha go to zero, and then you do recover. There are theorems telling you do recover fluid mechanics. So this is good because this is known. Now our job is to go from particles to Boltzmann. Okay, and then we'll just plug that into those theorems here, and we'll be done. How do you go from particles to Boltzmann? This is going to be a sketchy proof, but I think it will show you why Boltzmann pops up. For those of you who were sad enough to be here last Monday, I think I did that computation, which was a different one I did on Monday. So you can try see if you prefer this one. I prefer this one, but it's different. Okay, so I don't know if I prefer this one, but anyway, let's look at the n particle distribution functions. I have n particles, okay, and this Fn is telling me the probability that, well, the distribution of my particles at x1, x2, xn, okay, that's capital Xn, and v1, v2, vn, capital Vn. Okay, this is a function which satisfies a very easy equation, the UV equation, transport equation, because my particles are going in straight lines. Okay, transport equation with a boundary. Why? Because my particles do not overlap. So x1 minus x2 is always larger than epsilon. Okay, so this is a transport equation written in this phase space, which is a little bit horrible because it's imposing this condition here. So I need to put boundary conditions on this phase space. And the boundary conditions will just be that if I have two particles sitting on the boundary with velocities going out, I'm going to replace their velocities going out by velocities going in. Okay, so I impose this boundary condition to this transport equation. And so then I can solve this equation. And I'm happy, but that's not what I want. What I want is to get the Boltzmann equation. The Boltzmann equation relates to one particle, right? It's xv, it's not x1, x2, xn. So what I'm going to do here is just take this Fn and integrate it against all the particles except for number 1. So number 1 is just a choice because 1 is easy to write, but you could take any one because they're all undistinguishable. But let me just say I integrate between particles from 2 to n, and I keep particle 1. So now this is a good candidate to be a solution to the Boltzmann equation, since it's a function of t, x, and v. So let me call that x1 and v1. And so the claim is that this fn1 converges to a solution of the Boltzmann equation. So let's check that. So here it is again. And now to find the equation this fn1 satisfies, it's pretty easy. I have the equation on fn. Let me just integrate that equation from x2 v2 to xn vn and see what happens. Okay, so this is an exercise. The hard part of this exercise is, of course, commuting the integration and the derivative. Okay, but when you do that, you have this green formula which tells you that what comes out here. So you can try that at home. What comes out here is this guy here. We recognize, of course, the Boltzmann cross section. We call that. Right? So that's this is totally rigorous. If fn2 is smooth enough, fn2 is a two-particle distribution function. You can make it totally rigorous in a weak sense if you like, okay, but we won't do that here. So for the moment, I'm not cheating at all. The only thing I've done, which is not cheating, but I just decided to divide by alpha because Boltzmann told me to do that, and I multiplied by alpha here. And this cross section, this factor here is just because I have the volume of my sphere, which had been epsilon, right? What I've done here, I should say that a little bit more. What I've done here is that when I integrate my boundary condition, I have two particles sitting one next to the other. So particle x2 is sitting next to x1. That means this here, right? Omega is on the sphere. That's why I have epsilon t minus 1. But then I decided particle number 2 would be sitting there, but it could have been any particle, right? So I had n minus 1 choices. Okay. So if you agree with that, then this is perfectly rigorous. Okay, so here it is again. So this does not look exactly like the Boltzmann right-hand side, Q of FF yet. So we have to work a little bit on this right-hand side. So the first thing I'm going to do is use the boundary condition, right? Because this guy here, I don't really know it if my velocities v1 and v2 are outgoing. If they are outgoing, I have to replace those velocities by incoming ones. So let's do that. So this means outgoing velocities, because if you remember, which you maybe don't, omega is x2 minus x1 divided by epsilon. Okay, one more. No, yes, okay. Omega is x2 minus x1 divided by epsilon. So if this is positive, that means the time derivative of x2 minus x1 squared is positive. So I do have outgoing velocities. So then if I do that, I remember I define v prime 1, v prime 2 as the incoming velocities, like I was told to do, and then I apply the boundary condition. So if this is positive, I replace v1, v2 by v prime 1, v prime 2. If it's negative, I don't do anything. Is that okay? So again, there's no error here. I'm just using the boundary condition. Take limits. So just before taking limits, I'm just going to do a small trick, which is to notice that I could have replaced the minus here by a plus up to replacing the plus here by a minus. Okay, well, happy with this. But I'm happy because now I have this cross section, which is exactly the Boltzmann one. Okay. Now let's look at what happens when epsilon goes to 0. So I was told to take the limit n going to infinity with epsilon going to 0 with this Boltzmann grad scaling, remember? So what happens, where are epsilons? They're here and there. Now this is not rigorous. Okay, now is when things get a little bit shaky, but it doesn't matter. Let me take n goes to infinity. So this is true, this is going to 1. This is going to 0, and I'll just pretend I can remove it. So just pretend everything's regular, everything's continuous at least. Okay, so whatever goes to 0 goes to 0. And now I define like this a limiting operator, no more epsilons. Okay, acting on any function, I should remove the n's here, I guess there's no more n. This is a definition. This is my candidate to be a limit. And this tilde does not look like Q of F. Okay, so this is now the last trick, which is not a trick, it's an assumption. And for Boltzmann, it was an assumption. For us, it has to be at some point proved. But for the time being, let's make it an assumption. Assume that your two-particle correlation function at a limit when n goes to infinity looks like two copies of the same function. And let me call that function f. Let me say that function f is the limit of fn1, the one-particle distribution function. Right, I started with fn1. I'm very sad on the right-hand side, I have fn2. That was not expected, but yeah, well, it was expected if you've seen the movie before. But then you don't want fn2, you say, okay, let's just pretend it's a product of two fn1s. Okay, and then if I have a limit, I'm happy, I get exactly the Boltzmann equation. So what happened here? Where did we cheat? We cheated a tiny bit because we took limits in the argument here of fn1, but okay, maybe fn is continuous. Shouldn't be so hard to get by that. So maybe we can make a theorem out of this. The difficulty here is, first of all, this depends on n. So are you so sure that you have enough bounds to take limits? Okay, I assume that fn1 had a limit. Does it have a limit? I don't know. And then the other real problem is this here, right? I mean, here, Boltzmann is assuming that my particles, which are definitely not independent when n is fixed, because they are meeting each other quite often, he's assuming that when n is going to infinity, then they will become independent. Not always. I mean, it can't be that crazy. When people just have met, or have just met, they're not independent, of course. But you can notice here that because of the change of variables, this is positive, right? And so that means actually in those two situations, I'm actually computing f at an incoming velocity. Okay, so it should be true that you could, if you believe that if there are a lot of particles, if two particles see each other, they've never seen each other before, nor any friend that has seen them before, or any friend or any friend or any friend that's seen them before. If you believe that, then this should be true, and then you would get the Boltzmann equation. So, okay, so now the point is, can you prove a theorem? So the answer is yes. Actually, Lanford proved a theorem back in 1974, saying that if initially, so his theorem is much more general, but let's just assume initially all particles are identically distributed. Okay, so they all have the same distribution, which I call at zero. So initially, apart from the fact that they're not allowed to overlap, they're independent, according to this at zero. Then he proved that, sorry, you can't see Lanford because this thing here. So he did prove that the one particle distribution function converges to the solution of the Boltzmann equation. If your initial data f0, which I forgot to say, is continuous. I forgot all assumptions on f0, sorry. So f0 is continuous and bounded by a Gaussian, any Gaussian in velocities, okay? So uniform, bounded L infinity in space, decaying as a Gaussian V, continuous in space at least, then the one particle correlation function converges to the solution because initial data has the same assumptions we talked about before, the solution of the Boltzmann equation for a short time. The short time is t smaller than a constant times alpha. Okay, now those of you who remember what I said before might remember that alpha is going to 0 if you want hydrodynamical limits. Why to this day, no one knows how to go from Lanford to fluids, because Lanford just breaks down before you even can use the fluid limits. He also proves, actually it's part of the proof, everything is just one big package, that if you look at the n particle with small n fixed correlation function, it converges to n copies of the Boltzmann equation. So it's part of the proof that you do have this propagation of chaos assumption we had made in the formal proof. It's actually proved that you do have, as n goes to infinity, propagation of chaos. So we said Boltzmann was irreversible. We said the particle system is reversible. Why is that true? Meaning, why in the proof does irreversibility appear? And the reason is exactly because of that propagation of chaos assumption. What I said before is that two particles, when they meet, haven't met before. Okay, when I said that, I told you there was an arrow of time. Okay, so you can, that just explains why in the proof, at some point, I mean, if you're eliminating the possibility that two particles meet again, then you're doing something which is irreversible. Okay, so if you're not convinced with this, which I can understand, we actually wrote a paper with Thierry Boudinot, Laure Saint-Raymond, and Sergio Sumella, where we tried to make this a little bit more precise. So we wrote down Lanford's theorem in a horrible way, but this horrible way is irreversible. You can read the theorem and you see, okay, there is no chance you can write the theorem the other way. There's also no chance, because that's a good question you could ask, could you write Lanford's theorem and then when you arrive at time alpha, you say, oh, but look, I'm tensorized, so I could do it again. And arrive at 2 alpha and say, oh, look, Lanford tells me I'm tensorized, let's do it again. Okay, no, you can't, because the proof breaks down. Okay, this is I'm sort of telling you can't. You could try, of course, but what happens is when you'll see the new statement we have, you just can't go on. What you can do, which we found very interesting, is that and important in some sense, is that you can stop the proof before it's finished and do it again, which is not so clear. I mean, the proof is a semi-group, which is nice. I think it's nice because it's telling you that Lanford is telling you pick your initial data and then converge to Boltzmann. And that's not a nice theorem. I find more and more that if you give me a Cauchy problem theorem saying, give me U0, give me F0, I solve, that's not good. What I'd like is give me a F0, which is a solution to the equation, and then I can solve. Because it's a real F0. It's not just something you've picked up just for it to work, right? So, so Lanford was saying, give me F0, blah, blah, I can do it. Now we say, give me F0, I can do it, I can stop. And the thing I found here is a solution. It's not initial data, right? It's a real solution. I can go on. Not further, of course. I mean, you can improve the theorem like that, but it's sort of, for me anyway, it's reassuring that there is some kind of semi-group property in this proof. About that, I don't know if it's very understandable. Anyway. Okay, what I talked to you today for the moment was averaging on the initial configurations because I took distributions. What we actually do, well, what we can do anyway, and it's sometimes useful, and I won't be doing it explicitly, but I will be doing it implicitly in the rest of this talk, is actually I'll also be averaging on the number of particles. I don't want to keep that fixed, but I won't go into those details now. Okay, so as I said, the problem with the Lanford theorem is that it's only true for a short time, so we can't find fluid dynamics as a limit, which is very unfortunate, and we would like to do that. So there are just there are two results, as far as I know, where you can recover fluid dynamics, but they're very easy results in the sense that the fluid dynamics equations you recover are probably the most stupid in some sense equations because they're extremely linear. There's the heat equation, which is a nice, I mean, we all love the heat equation. That's not the most complicated fluid dynamics equation in the whole space or in the periodic box. So you can recover the heat equation and you can recover the Stokes Fourier equation. So just, I won't give any proof of that, but those are results we got a few years ago with Thierry and Laure, which consisted in preparing the initial data very much. So on the left-hand side, what you say is that you have your particle system, which is totally at equilibrium, nothing's happening. Okay, which is not very interesting. And then you say, okay, let me take one particle or two or three and put it somewhere else. Okay, so I put it the other side of the room and then I let it go. And then what you do is, when you do that, is you can take Lanford's proof for a short time and you find the linear Boltzmann equation, which I won't write, but which is even worse than linearized. So you take Boltzmann, which is the Q of FF, linearize against the Gaussian. Okay, that gives you 4 terms. Because there were 4 terms in Q of FF, so there were two products. And then out of those 4 terms, you kill 2. Okay. If you do that, that's called the linear Boltzmann equation, and it's very well known and very easy to prove that this linear Boltzmann equation goes to the heat equation. So what we did is use Lanford to go to the linear Boltzmann equation on a tiny time. And this time we could say, hey, but I know exactly what I look like at time alpha. I look like a Gaussian because nothing has happened because everything was at equilibrium or almost, and we can go again and again and again. Okay, by some kind of a pruning procedure. So we could get Lanford's theorem on a time which actually diverges with alpha, like 2 logs, okay, but it's gonna get worse. And so we were very happy because some of you have seen the movie before. So we were happy because getting that double log alpha gave us a long enough, well, gave us a bit of room to get the heat equation. And as a corollary, what you get is that that particle you move is going to satisfy Brownian motion. So it's nice because you started with a purely deterministic system of particles, and in the end, you got a Brownian motion. So in that case, you can do the whole program on this very easy heat equation case. And another case, which is maybe more interesting and slightly more difficult as well, is assume essentially all particles are close to equilibrium, very, very close. Okay. And then if you do that, you go to Lanford's proof and you get the linearized Boltzmann equations. You keep all 4 terms when you linearize. Easy exercise, this linearized Boltzmann equation goes to the Stokes Fourier equation as time goes to infinity and alpha goes to 0. And so in that case, up to losing an extra log, we were able to do the whole program. So if these guys go to infinity, are scaled like log, log, log n, then you get Stokes Fourier equations. Okay, so now just to finish, let me tell you a little bit about what can be done and what we'd like to do in this subject. So it looks like Lanford's proof has given all it could, I guess. I mean, it's hard to see how to improve the proof itself to make things global. What we would, I guess, would like to find at some point is the Navier-Stokes equations, incompressible Navier-Stokes equations. And so to improve the time of convergence, something has to be done, which is not just doing the proof again and trying to improve it just as it is. So one thing we tried to do just to think about this a bit differently was to say, well, now we have the Boltzmann equation, let's understand the error we're making around the Boltzmann equation, so fluctuations. Okay, so this is pretty well understood in some sense, in short times in general. And then one nice question was large deviations, meaning is there any chance that your particle system, instead of converging to the Boltzmann equation, will converge to something totally. So a large deviation principle tells you the probability of that should be exponentially small with epsilon, with some function depending on the time, some function depending on the function you want to get. So if instead of getting f, I get g, then the large deviation functional would be a function of g, depending on on f, of course. And so those two things are essentially understood as to some drawbacks, of course, for short times. And the idea is that to understand those things, new objects has to be understood, which we hadn't looked at before, people hadn't looked at before. And understanding those new objects maybe could help understanding something. So here I've mentioned the entropy cascade. What's that? Well, assume initially you have finite entropy, right? So your particle system conserves everything, it's reversible, nothing happens. The Boltzmann equation has entropy, which is decaying or increasing depending on the sign. So entropy is going somewhere. Okay? And so it would be interesting, I think, to understand where the entropy is going. And so it's pretty clear they're going into lower order corrections, like fluctuations, like all the other order corrections. So it's clear, but of course, I have no idea how to do that. So understanding those corrections, which we call, people call cumulants, are probably a good way of understanding maybe entropy cascades. In the case of the linearized situation I told you about a minute ago, we were sort of able to prove something which looks from very far like an energy cascade. So the entropy, if you linearize it, is f log f plus f minus 1. If you linearize that, it's f squared, right? So in the linearized situation, the entropy becomes the energy. And we sort of proved a kind of energy cascade in some sense. So it's not totally crazy to hope that maybe someday we'll get an entropy cascade. So I guess I don't want to, yeah, I should be stopping. I don't know, maybe should I stop now or not? You tell me who's the chair. Okay, so I'll just say one word about fluctuations and we'll stop there. So just to, if there's anything to take home here, the Boltzmann equation, you could understand like a law of large numbers actually, meaning that the probability that the empirical distribution I've written here is like f, the solution of the Boltzmann equation, this is actually essentially 1. Okay, so really the Boltzmann equation should be looked at as a law of large numbers for the particle system. And so, okay, I guess I probably will stop essentially now, maybe just the next slide. So fluctuations is what? If you know anything about probability theory, people tell you should rescale, multiply by square root of n, and then look at the same object. Okay, that's the fluctuation field, which is still something which is random. So expectations here are with respect to my initial data. So integrating against f0. And so the question is, if I zoom in like this, if I rescale everything, do I have a limit for this guy? So it had been conjectured by Spohn quite a while ago that yes, there is a limit. He even wrote down the equation on the limit, which is a stochastic PDE. So yeah, this we were able to prove, and I won't show you how. So I guess I'll stop here just to tell you that you can understand exactly what's happening here. And I guess the only thing I want to say here before I really stop is that you start with a deterministic particle system. You get the Boltzmann equation, purely deterministic as well, but the fluctuations are not. Fluctuations have a noise. Okay, and this noise, so Spohn had understood that for a long time. We really had a lot of trouble until it was done to understand why noise would appear and why what's in the dynamics gave you noise. And what gives you noise are recollisions. So the thing we were trying to kill for 10 years, recollisions were the enemy in the proof, are the enemy in the proof of Lanford theorem. All you do is geometry to say when two particles meet, they'll never meet again. It's a lot of work just to prove that some kind of that kind of a simple statement. But at the level of fluctuations, recollisions are really important. They're at the same level as as the initial fluctuations, and they give a noise. And so that we found sort of interesting. And I guess I'll stop now. Thank you.
Thank you very much, Isabelle, for a beautiful colloquium. Do you have any questions?
I have a question on a momentum equation and on the state law. Is there any hope of getting from such a model of particles the classical compressible Aléa equation for the momentum equation and a relation between energy, pressure, and density?
So from Boltzmann to compressible Euler already is essentially open as far as I know. I think it is known in the case of strong solutions, as long as you have a solution to the compressible Euler equation in this way, I think it's known, then the Boltzmann equation converges, strong solutions, but nothing is known at a weak level or an entropy level.
May I ask a question? My question is, what is the status of the theory when there are different groups of particles? For example, heavy and light, or particles, because when different particles of different mass collide, it is as easy to describe as when they have the same mass, but it is known that for fluid models, multi-fluid models, or it is a nightmare. So this is the reason of my question.
Definitely. So I have two answers. One is if you just put one massive particle in a bath of equilibrium particles, that's something we did with Laurent Thierry, you get an Ornstein-Uhlenbeck that works. That's not what you're asking, just one or two or three.
Okay.
Maybe
Which
12.
Is the star.
Exactly.
Yeah.
But then very recently, I don't think I wrote down the name, so I just have to think. There was Natasha Pavlovich and two other people. If someone can remind me the names, I'll be happy to say Miller and someone else, I think. Anyway, so the Blandford theorem has been derived for multi-species very recently. At least, I think 2 species at least.
Okay.
Which is, I guess, is the answer to your question. It's great. Yeah. And that's I learned about that last summer actually, or I think the preprint is just out. And so you have to work on, as you say, I mean, you have Blandford's theorem and you have it twice, right? And you have to understand how recollisions happen between, so it's hard and it works. Yeah.
I have a quick question. In your formal derivation, do you see this condition on the initial condition being bounded above by Gaussian anywhere in that argument?
In the formal argument?
Yes.
No, you don't see anything. And even, so let's see, you only see it actually when you start writing a proof, because as I said, you need bounds, right, to do something. And what happens is that your cross-section costs a V. And so once you start writing, you have your hierarchy of equations. F1 depends on F2, F2 depends on F3. So things are blowing up with V squared, V3 every time you add a new guy on the right-hand side. So that's why you need a Gaussian bound. But you don't see it at all in the formal.
There are no further questions. Let's thank Isabelle one more time.